Hey everyone! Ever wondered how AI is getting better at solving complex math problems? Today, we're diving into a groundbreaking approach that's pushing the limits of what large language models, LLMs, can do. Imagine an AI that's not just good at math, but exceptionally accurate and efficient, solving problems faster without sacrificing precision. That's exactly what this new research is all about. So let's break it down. The big challenge here is making AI better at mathematical reasoning. Why does that matter? Well, math isn't just about numbers. It's about logic, strategy, and step-by-step thinking. For AI to truly excel, it needs to master these skills. But how do you train a model to think like a human mathematician? The answer lies in a two-stage training process. First, there's supervised fine-tuning, SFT. Think of this as the AI's intensive study phase. Researchers feed the model thousands of math problems with detailed, step-by-step solutions. The goal? To push the model's accuracy to its limits. But here's the twist. They didn't just do a quick tune-up. They extended the SFT process for 10 full training rounds, a lot longer than usual. And guess what? This extra time made a huge difference. The model's problem-solving accuracy shot up, proving that sometimes more training is the key to breakthroughs. But accuracy alone isn't enough. What if the AI solves a problem correctly but takes forever? That's where the second stage comes in, reinforcement learning with GRPO. This is where the model learns to be efficient. GRPO, Group Relative Policy Optimization, teaches the AI to shorten its solutions without losing accuracy. It's like training a student not just to get the right answer, but to do so concisely. The result? Solutions that are faster and more practical for real-world use. What's amazing is how these two methods work together. SFT builds a strong foundation of accuracy, and GRPO refines it into something efficient. It's not a competition between the two techniques, it's a partnership. The study shows that after a long SFT phase, GRPO can cut down solution lengths by a significant margin while keeping accuracy high. The proof? The researchers tested their model on some of the toughest math challenges out there, including the AI Mathematical Olympiad, AIMO. Out of over 2,200 teams, their model ranked among the best. And they're not keeping their secrets. Everything's open-sourced so others can build on their work. So what does this mean for the future? It's a blueprint for creating AI that's not just smart, but practically useful. Whether it's solving complex equations or assisting in scientific research, this approach could make AI more reliable and efficient than ever before. Thanks for watching. If you want to explore the code and models behind this research, check the link in the description. And hit subscribe for more deep dives into the world of AI. Until next time, keep thinking critically and remember, even AI has to learn the hard way sometimes. Let's go deeper. How did researchers actually build this system? It starts with data. They gathered over 7,900 challenging math problems from sources like OpenR1Math 220K, focusing on questions even top models struggled with. They cleaned this data, ensuring each problem had a clear, correct solution. And when answers were missing, they used the model's own reasoning to fill the gaps. Think of it as curating a library of tough problems, each paired with the best possible answer. But raw data isn't enough. The next step. Training. The researchers used a two-stage process. First, they fine-tuned the model with a method called Supervised Fine-Tuning, SFT. Imagine teaching a student by showing them hundreds of solved problems, gradually improving their accuracy. They trained the model on 8 high-powered GPUs, tweaking parameters like batch size and learning rate to maximize performance. The result? A model that's way better at solving math problems, but it started generating overly long, wordy explanations. Here's where things get clever. To fix the wordiness, they applied GRPO, a second stage that rewards concise, structured answers. Picture a teacher giving feedback not just on whether a student got the right answer, but also on how efficiently they explained it. The GRPO system used 3K checks. 1. Format checks to ensure answers followed the correct structure, like boxing the final result. 2. Cosine similarity, to compare the model's reasoning to a gold standard solution. 3. Length penalties to discourage unnecessary fluff. The impact? Massive. On benchmarks like AIME and MATH 500, models trained this way showed significant improvements. For example, a 14B parameter model boosted its accuracy by over 5%, while cutting down the average solution length by nearly 20%. Even the smallest models saw gains, though the biggest improvements came with larger models. But here's the twist, not all problems benefited equally. The most notoriously difficult questions still trip the model up, showing that math AI still has a long way to go. Yet the two-stage approach proved its worth, balancing accuracy with efficiency in a way that could revolutionize how we train AI for real-world math challenges. So what does this mean for the future? It's a glimpse into how AI can learn not just to solve problems, but to do so with clarity and precision. Whether you're a student, a researcher, or just curious about AI, this work shows that the next generation of math-solving models isn't just smarter, it's more thoughtful too. Thanks for watching. If you want to see how this tech could transform education or problem-solving, hit subscribe. And drop a comment. What math problems do you wish AI could solve? Let's keep the conversation going. Imagine you're competing in a massive online contest with over 2,000 teams. Think of it like the Olympics of AI math problems. That's exactly what our model did, and it didn't just participate, it smashed the competition. On the public test set, it scored 29 out of 50, good enough for 4th place, and on the hidden private set, 28 out of 50, landing 8th. These aren't just numbers, they're proof that our approach is both powerful and consistent, even when the stakes are high. So how did we pull this off? The secret lies in a clever two-step strategy. First, we use something called supervised fine-tuning. Think of it as giving the model a bunch of math problems with answers, so it learns to mimic the right thought process. But here's the twist, we didn't stop there. After fine-tuning, we layered in reinforcement learning, a technique that rewards the model for thinking deeper and more efficiently. Together, these methods aren't just complementary, they're a game changer. The result? A model that doesn't just solve problems, it solves them faster with fewer steps without sacrificing accuracy. We tested it on some of the toughest math challenges around, like the AIME and MATH benchmarks, and even in the AI Mathematical Olympiad, a competition so strict that no hints or leaks are allowed. Our model didn't just hold its own, it proved it could thrive in real-world conditions. This isn't just about rankings. It's about building AI that's not only smart, but also practical. By balancing accuracy with efficiency, we've created a blueprint for the next generation of math-solving machines. Whether it's tackling complex equations or helping students learn, this approach shows that AI can be both brilliant and adaptable. Stay curious, keep exploring, and remember, math isn't just numbers. It's a puzzle waiting to be solved, and AI is just getting started.